Hello, welcome to my third one of these lessons on Newton's third law. I attempted to make this a little bit jazzy and it has just rendered it slightly more difficult to read. There's a reason I'm not an art teacher. So you should have completed the Newton's first law, second law, and we'll finish this little bit of this physics topic with Newton's third law. These three laws, you don't tend to get an awful lot of questions on them on their own. It's more about using the knowledge here to be able to answer or apply it to the stuff that we'll come to later after Easter now. So before we start looking at this, we are just going to have a go at this exam question from the assessment, because a few of you seem to struggle with it. So you were given to essentially this question, a rocket that had an upwards and a downwards force, and you needed to talk about these forces and then do a couple of calculations. This is pretty much as tough as these questions are going to get directly on Newton's laws, so nothing too scary, but I appreciate that these questions can look a little bit difficult. So it's got an upwards force and a downwards force, and the first question asked you to name them. So the upward force, this is what's driving your rocket upwards, and this is thrust. Any force that pushes something up in the air or pushes a car along the ground, something that's moving it forward, that's driving it forward, we can nice and generically call it thrust. Whereas the downwards force, that's what's pushing my rocket back down, trying to stop it taking up. That's gravity. Gravity is what's holding my rocket to the ground. Or you could talk about drag or air resistance as well. Either of those would be okay. Make sure when you're thinking about these or answering these questions, think what's actually going on. What's pushing my thing back? And what's my device trying to do? It's trying to go upwards. It wants to go in that direction. What's pushing it backwards? Okay. You're then asked to do a calculation on the resultant force. It told you that the upward force was 10,000, that the downward force was 8,000. So to find the resultant force, it was nice and simply taking this number here away from this number. So 10,000 minus 8,000 to get to 2,000 newtons. Okay, nice, simple enough question. And then the final question, albeit in a slightly more long-winded way than this, asked you to find out the acceleration of the rocket, having told you that the mass was 800 kilograms. Well, the equation it wants you to use is that for Newton's second law, so force equals mass times acceleration. Okay, so make sure you'd write your equation. You get a mark for stating that. Your mass, nice and simply, it tells you is 800 kilograms. Always check your units with this. You want it to be in kilograms. Your force, the bit that made this question a little bit tricky, is that you had to know to use the force you just calculated up here. So force is equal to 2,000 newtons, and acceleration is what I want to find out. So my equation, to find out my acceleration up here, I'm going to need to do my force divided by my mass. So I'm going to need to do 2,000 divided by 800, which comes out at 2.5 meters per second squared. Okay, this in an actual exam question would be 3 marks, so it's really valuable making sure you know this equation and making sure you're happy rearranging it. That's the case with all your science equations. It's just worth going over and over them until you're happy with them. Great. So that's done. Back to Newton's third law, and it's just worth recapping our other laws very briefly. So my first law was all about stationary objects. So that if the resultant force is 0, objects have 0 acceleration, so they must either be stationary or constant speed. And we use that to look at what terminal velocity was, remembering that when something reaches terminal velocity, the forces are balanced, the resultant force goes to 0, so acceleration goes to 0. Then second law was what we just looked at, which is force is equal to mass times acceleration. Okay, terrible handwriting there. So my third law is linked to these two. Okay, and it's the one that people are most likely to have heard of, because it's the one that is perhaps spoken about most commonly, and we might say it without not necessarily knowing what we mean by it. So the third law is every force has an equal but opposite force. So this is often said as every reaction has an equal but opposite reaction, and it's essentially what this means here. Every time you apply a force to something, that something applies an equal and opposite force. So if I take this pen and I throw it, I apply a force to it, it equals or applies that same force to my hand, an equal but opposite force. A nicer example of this to think about is if you lean yourself up against a wall, like so, because you're tired, had a long day of self-isolation and you're resting up against a wall, you are applying a force to that wall. That force is your weight, your mass, and you're pushing it against the wall. If that was all that was going on there, you would fall through into the wall. But as this law is obeyed, that wall pushes back at you with an equal but opposite force, and that's why you stay where you are when you push against the wall. Equally, when I put a pen on a desk, it is applying a force to that desk. Gravity is pushing it down onto that desk. The reason it's not pushed through the desk and doesn't dent it is because my desk is pushing back with an equal and opposite force. So if we think of a car accident and we think of you driving a car into a tree, this is my tree, make full use of my colours here, say full use, I drive my car into a tree, my car hits that tree with a certain amount of force, okay, and that force we could work out, couldn't we, because we know force is equal to mass times acceleration. Okay, so depending on how much I'm accelerating when I hit that tree, depending on the mass of my car, will determine how much force I hit that tree with. And if that was the only thing going on there, the tree would get damaged, it would get broken, but that would be it. But we know if you drive a car into a tree, it's not just the tree that gets damaged, your car does too. Hopefully we don't know that firsthand. And the reason your car gets damaged is because the tree applies an equal but opposite force. Okay, it pushes a force back onto my car, causing my car damage as well. Okay, and you could look at all of this and think to yourself, if this is true, if every object exerts an equal and opposite force, why do objects move? Why do we ever get movement? Why don't these forces just balance each other out and everything remains stationary forever? and it's because of this. If the force exceeds the mass, you get movement. Okay? So this force might be equal and opposite, this force might always be the same, but the mass of the objects involved is not. So I chuck this pen, I exert a certain force on it, and it exerts an equal and opposite force on me, but I weigh much more than the pen, and so I don't move. You can see this if you stand on a skateboard and you throw a brick off. You think of that, you're on a skateboard, you throw a brick off, you have applied a force in that direction, it's applied an equal and opposite force on you, and as a result your skateboard will move forward a little bit. Because you're on wheels, you can see that force exerting more, the mass is less of a factor in it. Okay, so this phenomena we can use to explain how rockets work, how rockets are launched, and it's quite a nice way of thinking of this, because you can see some good rocket launches online. So when your rocket is sat on its launch pad, like so, draw myself a rocket. Not the best rocket in the world. It is sat there and it is stationary because gravity is pushing down on it, its weight, and it isn't moving, but pushing back up is the friction, the launch pad, the ground itself is pushing back with an equal and opposite force, keeping my rocket in place. When you start a rocket's engines, we'll go at drawing a better rocket this time. When you start a rocket's engines, it releases lots of gas. Okay, and that gas exerts a force down, it's expelled, and it gives a force. Okay, that force being pushed out of your rocket, it applies an equal and opposite force to your rocket here. These two forces are equal to one another, and as a result your rocket doesn't move anywhere. Equal and opposite forces balance out and your rocket stays where it is. And if you watch a rocket being launched, you'll be able to see this. For a few seconds it stays exactly where it is, and then finally, if we go big for the final rocket, finally once that force becomes big enough, once you've got enough smoke going on there, enough gas being expelled from your rocket, this force, they're still equal and opposite, force 1, and you've still got this same force pushing back, but this force now is bigger than the mass of the rocket, and so it starts to move it starts to move that rocket upwards, and that's why it takes off. And rockets, this force just gets bigger and bigger and bigger, so the rocket picks up more and more speed until it makes it up into space. Okay, so the key thing to remember about Newton's third law is it's always about forces being in balance, and these forces can just get bigger and bigger until they overwhelm the mass of the object, and that allows movement to occur. The most important thing with all of these Newton's laws is that you're happy being able to state them, and you're happy being able to apply them to real world situations, that you're able to say why movement occurs or why a force is what it is. Okay, so please have a go at the questions. Make sure if you're not happy with anything on the questions, you re-watch this video or one of the previous videos, or you go back and look at the slides that are on your Google Classroom. It's not a case of you needing to test yourself what you remember. I want you looking them up. I want you searching things to make sure that you are keeping all the knowledge in your mind. Okay. Make sure you'll have a good Easter. You'll have a couple of weeks break from me after this, which I'm sure is very much to be looked forward to. I will see you after Easter. Hopefully these videos will have improved a little by then. Bye bye.